Hey students, in this video I'm going to go over how we model quadratic functions. First, we are going to talk about the type of regression that you could have when you analyze data. So here are some examples with images. The three types of regressions that you can have is linear regression when it follows a straight line pattern, quadratic regression when it follows a parabolic pattern, and parabolic just means like a parabola, but like only like part of it. And then exponential regression is if the data grows rapidly or decays rapidly. So it's all of a sudden up or all of a sudden down. And then again, the straight pattern is for the linear regression. So in these examples, this is again collecting data. People analyze the data once they have it in a graph, and then it's just predicting what type of regression is best. So for this one, if you notice that all of them are kind of like just going in a line, so that'll be linear. For this one, it looks like it's starting and then it increases rapidly, so that's exponential. And then for this one, it's a U-shaped graph, so that would be the quadratic. So that is just, again, a visual of the three types of regression that we can have. Notice that is just scattered points creating that pattern. It's not points that are connected creating that pattern. So then other thing to consider when we analyze regression is the R value. The R value that's calculated in our calculator. So if the R value is closer to 0, it's going to be considered weak. And what that means is that the data is spread out further apart from that prediction line. If the R square is closer to 1, then that meant a strong relationship, which means that the data collected, it's pretty close to forming a straight line. So when it's 0, that means there's no prediction. It just means that they're scattered all over. You can't really tell there's a relationship. Perfect relationship is when you have points that are exactly aligned or creating that parabola, and exponential, and then they match perfectly the line that was created. So in between values are either strong or weak. And I mean, halfway will be just the 0.5, 0.5. And so anything higher than 0.5 will be considered strong. Anything lower than 0.5 will consider weak. So for example, these two, if R squared is 0.81, that is pretty strong. And again, notice that you have these aligned forming that straight line. And then this one is 0.24, and that is weaker. They're more spread out. And then as far as how to get that, you're going to be given a word problem. You're going to determine what is representing X and Y. You're going to do the appropriate regression needed. And then you're going to write your line of best fit. So if it's linear, you're going to write the y equals mx plus b. If it's exponential, you're going to write y equals ab to the x power. And then if it's quadratic, you're going to do the y equals ax squared plus bx plus c. Keep in mind that in this unit, quadratic functions are focus. So you'll just be looking at quadratic regression with the ax squared plus bx plus c as your line of best fit. Then you're going to use that to predict new values. So let's practice with two examples. Here's the first example. A pumpkin tossing contest is held each year in Morton, Illinois, where people compete to see whose catapult will send the pumpkins the farthest. One catapult launches pumpkins from 25 feet above the ground at a speed of 125 feet per second. The table shows the horizontal distance that the pumpkins travel when launched at different angles. Notice that they're set up already as X, Y, input on the top, output on the other. Based on the angle, you get the distances. So using this data, we're going to write the quadratic equation. So it's going to follow the pattern ax squared plus bx plus c. So previously, we learned the steps of quadratic regression. Let me flip back to those notes real quick. And you follow the steps here. You're going to open a document and put the data in, label it X and Y. You're going to go to statistics, stat calculations, quadratic regression, and then you're going to get your values. Then you convert it into a graph to predict future values. So it's in your notes previously in this notes 3.5. So let's do that super fast. We open a new document. We add a list and spreadsheet. We are going to type this data, but first label this X and Y. And then we're going to have 20, 30, 40, 50, 60, and 70. And then 372, 462, 509, 501, 437, 323. So then menu, statistics, stat calculations, quadratic regression. Here we're going to say we're going to use the X for the X list and the Y for the Y list. And then here's the A, B, and C and the R square. So R square is 0.9999, which is almost a 1, which means this is pretty accurate prediction or data collected that almost forms a 1. A, B, and C values are right there. We can always add it as a graph. So control doc, up, enter. And then that's the equation that we could also just use already made for us. But if you want to round down your own, you can. The first 2 to 3 decimals placement values, I'll just copy it down from here. So we're going to have y equals negative 0.261 x squared plus 22.6x plus 23. So I'm going to just show you that the A value, negative 0.26, 1, 22.59, so 22.6, and then 23. All right, so that's the equation for that. And then now it's time to use the line of best fit to determine the following. We're going to estimate the maximum distance that the pumpkin will travel. That means that if you sketch it, there will be a maximum distance, because we know the X is the angles and Y is the distance. So they're looking for the highest Y value. So find the vertex, and then the Y value is the answer for this. So on our calculator, when we created the graph, we could trace this. We can go menu, trace, graph trace, and then just move to the right until we get the word maximum. So right here, maximum, so that is the point of maximum, 43.2, 511. I'm going to write it down. 43.2, 511. And if we interpret this maximum distance, we're looking at the Y value. So 511 feet, according to the table, distance in feet. That is the maximum distance that the pumpkin will travel. Then it's asking at what angle is it accomplished. So that's where the X value answers the angle. Angle is the X. So we can just say at 43.2 degrees. So that answers the angle that it was accomplished. Estimate what angle will result in the pumpkin not traveling. So then if we look at the data, we're seeing the pumpkin travel, travel, travel. So if it's not traveling, it's asking for when it lands on the ground. So we can go all the way till it tells us 0. And you can always also zoom out or just keep pressing this until you get to 0. Almost there. And we crossed it. So let's see, right there. So that's what it's labeling it as 0, 87.4. So we can say right here, what angle will result? And that was at 87.4. So 87.4 degrees. If we zoom out, we want to go menu, window, zoom out, and just kind of click until you see the 2 x-intercepts, or however you would like to see it. This other intercept, we can always do analyze and then 0, and then just create that left to right boundary, and it'll tell you right here the 0 for that one, which is this value right here, and then menu, analyze, 0, and then boundary line, and then that's the other 0 right there. For the maximum, you can also do menu, analyze, maximum, and then create a boundary line, and it'll tell you right there, maximum. So it sums it up for you if you analyze it in menu, analyze, graph, and then do those options. Okay, so the pumpkin traveled, reached its maximum, and then stopped at 87.4. Estimate the distance the pumpkin travels if the angle is 55. So this is you predicting when the angle is 55 degrees. So that's when x equals 55. What is the y value? That's what this is asking. So then we go here, we go to trace, graph trace, and if we press the number 55, it's already telling us that it's going to tell us when x equals 55. We press enter, and then it's 475. Somebody's knocking the door, but I gotta finish the video, so I'll ignore. Okay, so 475 feet. That's how much we have for that point in the graph. So 55, 475. Okay, I'll wrote it right here. So I sketched it, and then at that point of x equals 55, we have 475. So that means at 55-degree angle, the pumpkin will travel 475. All right, let's do one more example. The table shows how the wind affects the runner's performance in the 200-meter dash. Positive winds correspond to tailwinds, and negative wind corresponds to headwinds. The change of t in the finishing time is the difference between the runner's time and the wind speed s. All this information is for you to understand what this table represents. But if you kind of follow the pattern, x is on top, y is on the bottom. The input is the wind speed, and the output is the change in finishing time. So with that table, we're going to create a line of best fit for quadratic equation, y equals ax squared plus bx plus c. All right, so let's type that in. New document, don't save it. At least in spreadsheet, put an x in there, put a y in there, type the data. So -6, -4, -2, 0 to 4 and 6. Then we have 2.28, 1.42, 0.67, 0, -0.57, -1.05, -1.42. All right, once the data is typed in, you go Menu, Statistics, Stat Calculations, Quadratic Regression, put the X in there, put the Y, and then that's your ABC, and then the R square is 0.9999. So once again, the accuracy is super strong right here. To get these values rounded for you, you can always turn this into a graph. Control Doc, add graphs, press up, enter, and then here's the summarized version of this. 0.012x squared, 0.012x squared plus 0.309x. And then this last part with the E, if you go back to the data, it shows you that it's just 0.0004. That's what the E stands for, that you're moving the decimal 4 times to the left. So instead of 4.76, it's 0.0000476. So I'm going to write that down right here. Minus 0.000476. Okay, so this is the line of best fit. And then it's asking you for R square. So again, R square is right there. 0.9999. You can just round it. So it kind of rounds to 1. So is this strong or weak? This is very strong. It's almost 1. So it's very strong. Okay, and then we have now the prediction part, which is use the line of best fit to determine the following. Estimate the change in finishing time if the wind speed is negative 3 meters. So wind speed is that. And according to the table, wind speed is the x. So they're telling you x is negative 3. And they're asking you for the change in finishing time. Change in finishing time is your y value. So they're asking you for the y value. What is the y value when x is negative 3? So when we go to the table, we can trace and then just type negative 3, enter, and then that is the predicted y value. So we can also just make a sketch and say that at negative 3, we have 1.03. So 1.03 seconds, according to the data, it's seconds for the time. And then the last part is estimate the change in finishing time if the wind speed's 8 meters per second. So change in finishing time is again the y value. So they're giving you the x of 8. What is the y? So let's keep tracing, and now let's type the number 8, enter, and now it shows this. So if we were plotting a point, we're looking at 8, negative 1.71. So that corresponds with you answering that the change in finishing time is negative 1.71 seconds. All right, so hopefully this shows you examples of how to model quadratic equations and functions and analyze them.